Log on, tune in, find out. Another good idea from Cambridge.
All right, well, thank you very much. There will be no combinatorics today, and it will be a lot less concrete, but more general. And for some people, it's good that there is no combinatorics, and for some people, it's bad, and some people are omnivores, and they eat anything. So I will try to give an account of this complete moduli, of the construction for the complete moduli of surfaces of general type. So you have mg bar for curves, or mgn bar, and the idea is that there is this very similar moduli space where you replace curves by surfaces. And for many years, it was sort of a folk theorem where experts were confident that, sure, it exists. You can just look at this paper, and there is this moduli space. I don't know if I can consider myself an expert, but 15 years ago, I was sure that, yes, there is this moduli space. And then this confidence was shaken several times when people pointed out tricky things and some counterexamples and delicate points. And anyhow, by now, again, maybe it's just me, but I'm confident that all the holes have been plugged in, and there is a complete theory here. And also, the situation is much better in the sense that there is a book being written up by Janos Koller, still in the process of being written up. But it started as a multi-author project, and now it's a single-author project, which means that it will be completed sooner. Also, there is a survey by Janos Koller called Moduli of Varieties of General Type. It's available on arXiv. I gave a reference in the abstract for this lecture. So mostly what I will talk about is contained in that survey. And so whatever I don't explain very well, you can look it up there. So let's begin in the case where we have the analog of mg bar. So there is just a surface, but no divisors. It's not a pair, it's a surface. And the surface will be, it has semi-log canonical singularities, and it has this kx example. There is this condition. So what do these things mean? Semi-log canonical singularities I tried to define, but in the first lecture and in the second lecture. But so it could be non-normal. It can have some double locus, but only double locus in codimension 1. And then in codimension 2, there could be some triple points, and there could be some other singularities. And if you look at normalization, then that will fall apart into several surfaces. And now there will be a double locus. And this pair x nu plus double locus have to have log canonical singularities. Singularities. So for a surface like this, you can define this kx in the following way. So first, there is a z subset in X, and it's the codimension of Z is at least 2. And on the complement, the dualizing sheaf is invertible. This bad locus would include, so generically, in codimension 1, we have just normal crossings, so that's OK. That's Gorenstein. And so only several points in this case where there is some problem. So then we can take an nth power of this sheaf and saturate. And by saturation, we can just push forward if J is the embedding of this nice locus, x minus z into x, then this is our pluricanonical canonical class. So we require that this is an invertible sheaf. And we can call it Ox of n kx. So that's just a symbolical notation, a shortcut for it. And then the requirement is that this invertible sheaf so must be ample, and there exists some n. So these are the surfaces. That's the analog of stable curves in dimension 2. All right. Okay, so the moduli functor let's attempt and give a wrong definition. So this will be a failed attempt. So the first failed attempt would be maybe the M of S, I'll put a question mark, is, so these are families over S. These are just flat families F X to S, such that every fiber XS is a stable surface. So a surface like this with SLC singularities and the canonical class. And we'll fix something. Let's fix, OK. So this is sort of like a Hilbert scheme. And then Hilbert scheme splits up into connected components according to the Hilbert polynomial. So you probably, that's what you expect, that this is something infinite. But if you fix some numerical invariance, then you will have a nice finite part. And here's a very old example. It appears, I think, in Kohler-Shepard-Barnes paper in '89. There is a big problem with this. And the problem is that kx s squared is not constant in flat families. And let me show you this easy example. Here's the example. So you consider surfaces xt. These are just Veronese surfaces in P5. And the canonical class, if I'm not mistaken, then for P2, the k squared is 9. And then you consider a different family, and these are P1 cross P1 embedded by a sheaf of type 1, 2, again embedded into P5. And here k squared is 8. And so there is one family and another family, and they have a common degeneration, flat degeneration. So both of these families flatly degenerate in nice flat families to the same surface. So there's in the moduli, well, just in P5 you deform these surfaces. And here's your xt, and here's your xt prime, and here's x0. So the construction is the standard construction, which is the deformation to a cone. Deformation to a cone. So in this Veronese surface, in that P2, you have a hyperplane section. A hyperplane section is a conic. So the deformation to a cone is you can deform to a cone over that hyperplane section. And the same conic is a section of degree 4. I'm sorry. Right. So h squared equals 4. So it's a curve of degree 4, and you degenerate to a cone over that. And on the other hand, this hyperplane section also has degree 4, and it's just the same conic. And so you can deform this surface to a cone over a hyperplane section. And these are flat degenerations, so nothing really tricky. So this is another family. And so something is very wrong here, you know. So this is not a good functor. So in the good functor, this problem should be fixed. And the problem here is that, of course, if you have some projective family xt, and you have LT, so you have some L and an invertible sheaf. Then LT squared for surfaces must be constant. So the point is that these canonical bundles or pluricanonical bundles, none of them fit into a nice invertible sheaf. So we have a problem. Now you may, I don't know if anybody noticed, but P2 is not a surface of general type. So, also P1 cross P1. But that's immaterial, because what you can do, you can just add some very ample divisor which does not pass through singularities and look at a ramified cover. So just add, in a family, add some ramification divisors away from the problem, and then just look at, say, 2-to-1 covers. And then those covers will have ample canonical class. The singularities are nice. They're canonical even, I think. And all right, so the correct functor.
So this is something that you want, or has to be?
So see, what would be the, for a Hilbert scheme? You fix the Hilbert polynomial, and then you have these open and closed subsets. And here, k squared, our polarization is given by the multiple of k. So here we would fix the Hilbert polynomial of this nkx. We would probably choose some n, and then fix the Hilbert polynomial. And in these flat families, it's not constant. So that Hilbert polynomial for nkx is not constant.
So your objection is that you couldn't construct this moduli space as a JIT quotient of some Hilbert space? Is that?
Something very disturbingly wrong with this. It's, you know, we had 20 years to get used to it, so not very disturbing. But
I mean, is it possible that that's an okay functor and it's just the wrong thing to ask for k squared to be fixed? Maybe some other polynomial.
So if you remember, in the good properties, I had these 5 good properties, and I listed them again. And the property number 1 was polarized. It is the right thing to work with polarized varieties, right? And also, I needed all these 5 properties to apply that method, the method number 4, construction of the moduli space. So the polarization is given by the multiple of kx. It should be flat. This polarization has to be constant somehow, have the constant numerical invariance in families.
I mean, you need that to construct the moduli
Okay,
space.
that too.
the way
All right,
that
I'll agree with that. So this moduli space is constructed by using Hilbert scheme, so using ordinary polarized varieties. And so this polarization will coincide with nkx. But if I have this example, then without a correction, I cannot apply Hilbert schemes. So solutions, there are 2 solutions for, so there are 2 solutions to that problem. And one is, people call that phi of x, functor, and the other is Kohler's functor. So what's the physics functor? So we will fix some n, an integer, and we will look at surfaces with nkx, so with O of nkx invertible. And the functor will be like this. So mn bar of S will be still flat families, but they will be polarized families, XL, where L now is invertible, such that for every S, a point, this LS is isomorphic to O XS of NKS. So we force a polarization, and this polarization on every fiber, it coincides with that pluricanonical polarization. And so that's a lovely functor. It's, that problem is solved. Right, so just the idea here, a simple idea, is that flat families are not good families in this case. These are good families.
Is the small n equal to big N? What's the relation between small n and big N?
They're equal. So, okay. And then there is a functor mk bar. And so k stands for, k is not an integer. Kohler's functor. And so these will be flat families. X to S, such that for every n in Z, omega x over S to the n. So that's, let's give another name to this, omega x to the n. So this is flat over S, and the restriction of it to every fiber is omega xs to the n. So to define this sheaf, what I needed was that there is some codimension 2 bad subset. So outside of codimension 2, everything is nice. And so in the family, again, we just have this codimension 2 bad subset. So these are families of points. And outside of it, we have an invertible sheaf. The varieties. There is a relative dualizing sheaf is invertible. So that makes sense. So the difference here is that we fix some n and just look at this n. And so Kohler, he long insisted that all of them should vary nicely. Not just the multiples where nkx is Cartier, but all of them. So.
But you still require that.
Right. And every xs is stable surface. SLC singularities, kx is ample.
No, but I still require that some power is invertible.
So for every individual surface, there is a power. And then in an open neighborhood of that point, for all of them, this will be an invertible sheaf. But maybe for different surfaces, different multiple. Okay.
So there's a slogan which I learned from Nick Shepard when he was my graduate slogan that says that forming omega to the power of n commutes with base change.
Great. Great.
So,
Let's put that. And formation of omega x s to the n commutes with any base change t to s. So you do a base change, you have a new flat family, you can form this sheaf, and on the other hand, you can pull back the sheaf. They must coincide. This is a particular instance of this property when you base change by just including one point. All right. Now the good properties. So the way I try to present it, the first two lectures were as follows: that if you have those 5 nice properties, then it's more or less automatic that you have a moduli. There's the standard method that you apply, which is based on Kilmore paper, and it's very little work. So all the work goes into establishing the 5 nice properties. And let's see for either of these functors how that works. So polarized, we have a polarization, but with this little twist that you have to fix a multiple. And there is a question: is there a universal multiple that applies to all surfaces? But we have the solution. So this is a canonically polarized problem, bounded. So bounded. So here we have a fairly old theorem from '96, which says that if we fix kx squared, if we fix this one constant, then there is a universal n such that O of nkx is invertible, and the family is bounded. The family of such surfaces is bounded. So there is a, I can put it this way, such that this is invertible and very ample. So all these surfaces fit into one, can be parameterized by one big Hilbert scheme. It's a fairly technical result. There are 2 versions. There is also a version with Mori. I don't remember the year. A couple of years after that, which is more constructive. So there are some explicit numerical bounds that are given. All right, so that we have 1, we have 2. Finite automorphisms. So one needs finite automorphisms. Here there is an old result of Ueno, I think. It's in his book on algebraic geometry. And it says the following. It says something like this. Suppose y is non-singular and d, so projective, and d is normal crossing divisor, and ky plus d is big. Then the automorphism group of this pair is finite. And so the point for this is, let me just give an idea for the proof. It's even easier in our case. So we have a canonically polarized surface. let's just take a look at one canonically polarized surface. So we have this sheaf, which is very ample. So the automorphism group is going to preserve this sheaf. So therefore, this automorphism group is an algebraic group. It's subgroup of some PGL. On the other hand, if there is a, so it's either finite or there are some one-parameter subgroups, such as GM or GA. And in that case, the whole variety must be ruled. And if you just have a surface, say, of general type without any boundary by itself, if it's of general type, it cannot be ruled. And here the argument is just a slight generalization of that. So it cannot be ruled in the sense of these pairs. Anyhow, there is a very old result which is immediately applicable, and so that's not a problem. We apply it, of course, to the resolution of singularities, and the divisor D is everything, the boundary, so to say, the exceptional divisors. Now, and if you have several irreducible components, then you apply it to the normalization to every irreducible component. And so the automorphisms here are finite, and there is only finite permutation group. Okay. Local closedness. So that's a delicate point that was overlooked for a long time. And local closedness. So you need to know the following. So suppose you have just a flat family, and that flat family could be one of those bad examples. And then just flat. And then we'll say this is S. And then you have something T, and you do a base change, xt, and you ask when is this a good family? So in the Kohler's version, there is no L. You just literally ask after the base change, when do you have a family like that? So that this formation of the NKX commutes with all the further base changes. And local closedness means that there exists an S prime locally closed subscheme. So it's a disjoint union of some S prime I. Each of them is local, comes with a locally closed embedding. And so your base change is nice if and only if it factors through that universal S prime. So this was solved only recently by Kohler. And there is a paper, maybe it's even published, it's called Hulse and Husks. And again, this is one of the references for this talk, so you can look it up. Again, it's fairly technical, but that's the assertion in this theorem, that the theorem about, this is an immediate corollary of the main theorem in that paper. Uh-huh.
So why don't you want it actually to be open?
It's not open. It's not open. So it's what happens in that case? If you think of that example, in that example, say this is my family, right? These were family XTs. These were families XT primes, and this is X0. In this case, the locally closed subscheme looks like this. So everything is nice if you base change to one of these families. I'm sorry, the other way. So everything is nice if you base change to the family xt. In the family xt, the k squared was 9. This is where it was constant, where there was not a problem. On the other hand, if you base change to anything here, if you just exclude that problem point, then it's still a nice family. It's just the whole thing is bad. So this locally closed subscheme, that's how it looks. It's S1 prime disjoint S2 prime. And S1 prime is open and S2 prime is not.
So the thing of like the condition on each closed fiber is an open condition, but the additional condition on the family makes it
No, so this condition on the fiber is not open. Let's see what. So you look at any family, and it's either good or bad. So there are two possible outcomes here, true or false. And this was a bad family. So this family does not satisfy, is not a member of this functor. Okay? But anything that's obtained by a base change which factors through this subscheme is good.
Conditions, there are two kinds of conditions. There are conditions on the fibers and on the family.
That's right.
And the condition to be a stable surface, I guess this is an open condition.
See, stable surface is that nkx is Cartier and ample. So you want, if you say it's an open condition, then you say nkx varies as an invertible sheaf. That's false. So that's not true. In this bad family xt prime, the family of this pluricanonical nkx is not a flat family. If you wish, in the threefold, the canonical class is not Q Cartier. So on every fiber, nkx is Cartier. In the family, if you take nkx for the whole threefold, it's not Q.
Right. So that's what I'm saying. Like the condition on the fiber itself is satisfied, but not for the family.
That's a condition on the family, which doesn't make sense for a single fiber. So, but just the condition that it's SLC and ample, that was satisfied in the whole family. Right? All right. So maybe I will not attempt to explain too much more about that paper. So he defines something, a generalization of this, there is yet another notation here. And this is a hull. So he defines this hull more generally, and the paper specifically treats the formation of the hull in families. And the main result is that for this problem of forming a hull in a family, there is a fine moduli space, and it's locally closed. All right, number 5. Number 5 is properness. I spoke about this twice. So I gave you, in the first lecture, I gave you an example with curves, and then in the second lecture, I tried to explain it more generally using MMP. Let me add a detail which I skipped last time for brevity, and let me fill it in. So there are two cases here. The first case is when you start with a family of irreducible surfaces. So there is xt, this family. So x is a threefold. And if you remember, the to construct the stable limit, what you do is you pick a stable model of this, and then you apply relative minimal model program. So you find the relative canonical model. So you go to X canonical model, and this then the central fiber, that's the limit. And this limit has SLC singularities, and Kx is ample. So it's in our category. You find a limit in our category. And moreover, this problem does not show up because in the minimal model program, you apply it to a threefold. So on a threefold, some multiple of the canonical class will be Cartier. And therefore, so the bad case is when fiber-wise you have Cartier, but in a family it's not Q Cartier. No multiple is Cartier. Here it just doesn't show up. All right, so that's one direction. What this proves, this construction, it proves completeness. So it proves that to any family you can construct at least one limit. And then to prove separatedness, if you say it very quickly, then you just say that the functor is separated because the canonical model is unique. And so if you have some variety with relatively ample canonical class, then it's the canonical model of any resolution, of any nice model. But what you need here is the following statement. What you need is the following statement. Suppose X0 is SLC. Then you need to know that the whole threefold, the whole family, is log canonical. So you need to know that X is really, if you only have a family such that every one parameter family, where every fiber is nice, you want to know that this threefold is log canonical. And so then X is a relative over S canonical model. So then you can apply this statement that the canonical model is unique. So this is a very non-trivial implication. This implication is called inversion of a junction. It was Shakurov-Kolar's conjecture. It was in that volume in the Asterisks on threefolds, birational geometry of threefolds. It was proved under some special assumptions in some special situations, which you don't have here. And so that was also a serious problem. And it was solved by Kawakita. So he has a paper in Invenciones trying to think, I think 2006 or so, with this title, and so he solves. That's where this problem is solved. All right. Then.
Sorry,
So
does this to have canonical singularity?
Here's how a junction works. If you take kx plus x0 and you restrict to x0, then that's by a junction, that's kx0. And so what you should be comparing really are pairs now. This pair versus this pair. And when you do the minimal model program, this is not how Kohler and Shepard-Barron did it in their paper. Their argument is somehow with canonical singularities. But I think this is a much cleaner way. So here the statement you want is that this surface is SLC if and only if this pair is LC. So that's the inversion of adjunction. Inversion of adjunction, there is a numerical implication here, but also an implication about singularities. So further, what about the families with non-normal generic fiber? So this argument with the minimal model program, it applied to a threefold, and the threefold was normal. And therefore, the generic fiber was irreducible and normal. But if in our functor now we allow arbitrary families, including the families where every fiber is non-normal. And so what do you do? Of course, then an obvious idea here is to look at the normalizations, right? And then degenerate each of these surfaces, each of these pairs, and then prove that it all glues back nicely. That would be the thing to do. And when you glue along these curves. And so what you need to know is, again, it's this junction formula, basically. If you have a canonical model for a pair, you need to know that to every curve that restricts to a canonical model of that curve, of that family of curves. So with the curves, it's a fairly straightforward argument, but now the triple points will require that you do it carefully and you make sure there are no gluing problems along at those points. For surfaces, one uses the threefold geometry. So one knows how the canonical threefolds look at the triple points where three divisors with coefficient 1 intersect. If it's a Gorenstein point, then it's a smooth point and normal crossing divisor. But if you just try to extend it to higher dimension, say to families of three-folds, four-folds, etc., then this is another delicate problem which currently does not have a solution, I believe. So it's an abstraction to extend in this just in a straightforward way. Okay. So with these things out of the way, then I can just wave the magical wand and say the standard method number 4 applies. And you construct the modular space as follows. You fix some big capital N so that all of your divisors are very ample, then your surfaces are parameterized by a Hilbert scheme. Inside of this Hilbert scheme, there is a locally closed subscheme that precisely parameterizes the nice families. And then you just divide by an equivalence relation, which is the PGL action, PGLN action. And because properness, that's number 5, plus finite automorphism, number 3, that imply that the group action is proper. And your groupoid is finite. And then Kiel-Mori apply. And that gives you the coarse moduli space. That coarse moduli space, as a result of general theory, is only an algebraic space, not a scheme. But then there is another old paper which was very influential for all the developments here by Kohler, called projectivity of complete moduli. That paper implies that this moduli is in fact a projective scheme. The idea of that paper is that if you have a moduli problem which is canonically polarized, so it's for this canonical polarized by some intrinsic polarization, such as this. And you already know that your moduli space is a proper algebraic space. Then it's automatically projective. So what you do, you just construct an ample invertible sheaf on your moduli space explicitly. That invertible sheaf is, let me just say what it is. In this case, you push forward these sheaves by take a very large multiple and push them forward and take the determinant of that. And this is ample on the base. Coming from Hodge theory, precisely.
That means it does work in positive characteristic?
It does not work in positive characteristic. That's right. Also, definitely his proof is with Hodge theory. And the proof, so the ampleness is checked by using Nakai-Moishizon criterion. And so you need complete. So you need proper. Only then it applies. But you get a projective moduli.
What's the instruction to constructing these moduli spaces in GIT?
Abstraction is our complete inability to check Hilbert-Mumford criterion for anything but curves.
There are counterexamples. I don't understand what the counterexamples are. But Carl and Ship and Barron have told me many times that GIT just doesn't work.
Right. Here is the supposed counterexample. Let me just try to account for that. So in Mumford's GIT book, there is an inverse lemma. It's somewhere in the first pages. And it says that if the quotient is projective, then the points were semi-stable, something like that. And on the other hand, he proves that in his paper, Mumford, in his paper projectivity, stability of projective varieties, I think, in that paper, he proves that if you look at a stable surface in this language, and even with normal, then if it's stable in the sense of GIT, then the multiplicity of every singular point is at most 6, something like that. And so that's a counterexample because these surfaces, of course, can have multiplicities of arbitrarily large, can have singularities of very large multiplicity. And the way, right, so this is, we had many discussions about that. So the way Vivek explained that, and he explains it in his book, supposedly, is that this GIT depends, it's quotient by GL, and therefore there is a choice of polarization. And so for some polarizations, this could be a semi-stable, linearization, I'm sorry. For some linearization, it could be a semi-stable point. For another linearization, non-semi-stable. And in the statement of Mumford, in Mumford's paper, he looks at a very specific linearization. But you can pick a different one. And supposedly that's what Vivek does in his book.
So I would say like that Vivek, I mean, if I remember correctly, he never he never checked that his one parameter criterion for stability. But somehow he is able to still produce the GIT quotient, and then say like a posteriori that the points were actually stable.
So in Vivek's book, the moduli are not complete, and then there are only 4 varieties with canonical singularities. And
but for those, like a posteriori, he proves
that they are GIT stable for some specific choice of linearization, and I think he even writes it down. And so that's the solution. But really, GIT, as I said earlier this week, GIT for stable curves. This Hilbert-Mumford criterion was proved only like last year by Jun Lee and his co-author. So otherwise, for many years, only smooth curves were checked, and also Giesiker did something for normal crossing surfaces. And otherwise, it's extremely hard to use. And so when someone applies, GIT successfully, then we'll see. But so that's a way around that situation. Okay, let me get to the second part, where you add now B.
So what you set up now, it applies to the both Vivek functor and...
It does. Mm-hmm.
Is there a relation between the two functors?
Right. So I think it's clear that every Vivek let me see. If that family is flat, then in particular for every capital N like that, you have a flat family. So there is a map from MK to every Mn, and there is a map from Mn to M, say 2n, 3n, 4n. Here you have infinitely many functors, potentially infinitely many solutions, and they're like a tower. What was the discussion about that? So Kohler showed that in characteristic P, you really can have infinitely many non-isomorphic ones. That if you look at the local deformations, they are different. They depend on that. And then in characteristic 0, I think the one somehow proved that there are only finitely many.
But is this V case, sorry, inverse the letter Vn?
No. It's here's the MK means you look at all of this, right? And Vivek's means that you only look at multiples, and so this is n. And for 2n, you look even at fewer, right? So if as n is enlarged, you sort of lose more and more information. So if you look at the inverse limit, maybe you lose all of it. So definitely MK is not the inverse limit of Vivek's. All right, so number 2. Here is another disturbing example that was first pointed out by Paul Hacking, I think, and then Brendan Hassett wrote it up. Here's the problem. Now suppose we work with pairs now. So we really want to generalize MGN bar. So instead of n points, we will have n divisors. and maybe even with weights, so with coefficients. And look again at this construction of this proof of properness, at the construction of the limit. So you have a family, and in that family, it's a threefold family. So you have family of a threefold family of surfaces with curves. So D is a surface. So what the MMP gives you, it gives you that this divisor is Q Cartier. But it does not imply that individually that both of these are Q Cartier. And indeed, it's very easy to produce an example, a very simple looking example, and where this sum is Q Cartier, but this is not Q Cartier, this is not Q Cartier. But what this implies when this happens, so if D is not Q Cartier, then D0, it's a subscheme, it's a closed subscheme in X0, closed subscheme, has an embedded point. So that's a very bad news somehow, because you start working with pairs where you have a variety and a divisor, but your limit, your natural limit, is a pair where you have not divisors, but subschemes with embedded points. Maybe I'll try to draw this picture quickly. That this has its example. So you start with a family like this. This is just P1 cross P1. You have a threefold, just Cartesian product. And then in here you pick a curve of type 2-1 and blow it up. And so then in the central fiber, you now have two irreducible components. One is still this one. The other one will look like this. And it will be an F4 surface, Hirzebruch surface. And then pick a curve like this. So on these components, it's just two fibers. On the other components, so there are. This is the curve of intersection. So there are these 4 points of intersection. You just pick a generic curve. You can write it down. So that together, that's a curve. That's your curve B. Okay. And then smooth it out. So this curve, you can look at the deformation properties of it. It can be smoothed to a non-singular curve somewhere else. So all these curves, they have arithmetic genus, I don't remember what, say 36. Okay. So now this will be, this family, this threefold family is not the one we're looking for. So let's say, put a tilde here. Now contract it, contract this component now. In the central fiber, just take this P1 cross P1 and contract it to a point. Then in the central fiber, in this curve F4, you're contracting an exceptional surface, an exceptional section. So you get a cone over a quartic curve, and your divisor now looks like this. And you compute an arithmetic genus of this curve, and it's different. It's different. So it's not the one that you had before. And so therefore, what happened now, this is really the family that appears in the counterexample. So you have you have a family of these B's, so these are BT, and on the generic fiber you have one arithmetic genus, and on the special fiber you have a different arithmetic genus. So that cannot be a flat family. So, but of course, for any family, for any projective family, there is a unique flat limit in the Hilbert scheme. It's just this flat limit is a scheme, and this scheme has an extra nilpotent sitting at that point. So it has an embedded prime. So that is truly, bad news, it seems, because now what? So what's the solution? So are we supposed to work now with pairs where BIs are not divisors but are schemes? That's how do we deal with that? So the birational geometry is not set up like that. It's really for pairs with divisors. The solutions are as follows. So there are several solutions were proposed for this problem. First is if all your coefficients are 1, then this never happens. So what in this example, kx plus 1/2 b is Q Cartier, but b is not Q Cartier, and kx is not Q Cartier. But this linear combination. So it's for a pair where the coefficient is 1. And so I proved in a paper on limits of stable pairs that this situation just does not appear if you work with coefficients 1. And then Kohler, I haven't looked closely, but I think in some paper he proves that for as long as the coefficients are strictly greater than 1/2, then this does not happen. So you can stay with your ordinary setup of pairs, variety plus a divisor. Then another solution is this. So suppose that BIs are linearly independent over Q. So they're real numbers, and no linear combination is integral. So what MMP tells you? It tells you that kx plus b is R Cartier. And so if no linear combinations are integral, then that implies that every BI is Q Cartier. There are no cancellations. And so if your coefficients are generic, then again, that problem does not show up. And then, of course, you can combine this, and that works. So if some of your coefficients are large, and the others are Q linearly independent, then again, that's fine. The third solution, which I proposed, was to replace divisors by branch divisors. So branch varieties are, what are branch varieties? Branch varieties are, what's a branch divisor? So if you have, here's the branch divisor, that's your variety D, and a branch divisor is a curve with a finite map. But it's a reduced curve with a finite map. And so Knudsen and I constructed this moduli of branch varieties, and you can apply it to construct this moduli of branch divisors. The point here is this. In the Hilbert scheme, where this problem showed up, Hilbert scheme parameterizes embedded subschemes, but with nilpotents. You can replace that by non-embedded things, but without nilpotence. And there is a moduli for that. And so that works. What happens in this particular example is the following. So if you, instead of contracting this whole component to one point, you can do it in 2 steps, and you can first contract it just in one direction, one ruling, to a curve. And then your curve will be like this. It will be nodal. And then, so that's a branch divisor. It's a nodal curve. This family is flat. They have constant arithmetic genus. But this is not a divisor here. It's not embedded. Instead, it has a finite 2-1 map. So at this point, it's a 2-2-1 map. So that's the solution. And branch divisors. And then the final solution that I will mention is this. So if you have kx plus b, so you have this pair xb, and b is effective and integral. Then you can encode this pair. You can encode in the following map. You can encode this divisor b by saying that this is a map from this sheaf to this sheaf. So that's your MB. So the divisor can be encoded in a map like that. And these are supposed to be invertible, and this we can replace by just the power of dualizing sheaf, not the hull, but just this power. And so you can encode B in saying that you now look at pairs together with a map of sheaves. And that's your modular problem. You look at pairs with a homomorphism, with a sheaf homomorphism. And then again apply hulls and husks and prove that your functor is locally closed. So that's Kohler's solution. All right, so let me stop. So since I'm the last speaker, I guess I have to